Something has been quietly running inside the human brain for millions of years, watching, modeling, correcting, and never quite stopping. And most of us never notice it's there. Self-awareness, as neuroscience understands it, is not a feeling. It is a system, a set of brain regions working in concert to generate a continuous, updating model of the self. Not a soul, not a ghost in a machine, but a measurable biological process with its own anatomy, its own timing, and its own peculiar vulnerabilities. The network most responsible for this is called the default mode network. It was discovered almost accidentally. Researchers scanning resting brains in the late 1990s noticed that certain regions didn't quiet down when the subject was doing nothing, they lit up. The brain, it turned out, was most active in self-referential thought precisely when no task was being asked of it. Marcus Raichle at Washington University named this pattern the default mode, and the science of self-awareness was never quite the same afterward. If you've ever let your mind wander and found yourself thinking about yourself, that was it. Like and subscribe, it helps this channel reach more curious minds. The default mode network is not one structure but a coordinated cluster. The medial prefrontal cortex sits near the front, handling self-relevant judgment, questions like whether a word describes you, whether a situation applies to your life. Further back, the posterior cingulate cortex acts as something like a contextual anchor, linking present experience to memory and personal history. Together, they generate the sense that all incoming experience is happening to someone in particular, to you. What makes this strange is that the brain does not have direct access to the world. It receives signals, electrical impulses translated from light, pressure, chemistry, and motion. The self-model it builds is a construction, an inference, not a direct readout of reality. The brain assembles what it calls me from fragments, and the assembly is so seamless, so fast, that it never feels assembled at all. Have you ever caught yourself thinking something and wondered where that thought came from? There is a measurable delay between a neural event and conscious awareness of it. The neuroscientist Benjamin Libet demonstrated in the 1980s that the brain shows preparatory electrical activity, called the readiness potential, several hundred milliseconds before a person reports deciding to move. The conscious sense of intention appears to arrive after the process has already begun. This finding has been contested and refined many times since, but the core observation, that conscious self-awareness lags slightly behind the neural events it claims to narrate, has held up across decades of replication. The self, in other words, is always a little late to its own story. The specific brain region most strongly associated with the capacity for self-awareness is the medial prefrontal cortex. Patients with damage to this area often lose the ability to recognize themselves in photographs, to attribute mental states to themselves, or to distinguish their own perspective from another person's. They remain intelligent, verbal, and capable in many ways. But the particular thread of selfhood, the sense of I as an ongoing agent, becomes frayed in ways that are quiet but deep. Neuroscience also distinguishes between two layers of self-awareness that operate differently. The first is minimal or bodily self-awareness, the basic sense that this body is mine, that these sensations belong to a subject. The second is narrative self-awareness, the ongoing story the brain tells about who that subject is over time, across memories, through change. These two layers can be disrupted independently. A person can lose one while the other remains largely intact. The minimal, bodily layer appears to be older in evolutionary terms. It likely predates language. Certain brainstem structures and the insula, a cortical region folded deep inside the lateral sulcus, contribute to this more primitive self-signal. The insula receives information from the body's interior and helps create what researchers call introspective awareness. The dim, continuous sense of the body's state from the inside. It is one of the roots from which the fuller sense of self eventually grows. What runs through these early regions is not thought exactly. It is something quieter, a kind of ongoing registration. The anterior insular cortex, in particular, appears active when people become aware of bodily sensations, emotions, and, intriguingly, moral discomfort. It is one of the few regions implicated in both physical self-awareness and social self-consciousness. In neuroimaging studies compiled across multiple labs and reviewed in Nature Reviews Neuroscience, the insula consistently activates when subjects reflect on themselves in relation to others, not just on themselves in isolation. Self-awareness, even at its most basic level, carries a social dimension baked into its biology. There's something almost settled about that. One of the more surprising findings in self-awareness research is that the default mode network is not idle during external tasks. It is actively suppressed. When you focus on something outside yourself, task-positive networks increase their activity and the default mode quiets. But the suppression is never total. A low hum of self-referential processing continues in the background, monitoring, updating, occasionally pulling attention back inward. The self-model never fully switches off. It waits. This is built for bedtime listening, the kind of science the mind can hold quietly. In the 1970s, the psychologist Gordon Gallup Jr. noticed something unexpected while observing chimpanzees that had been marked with dye while sedated. When the animals woke and encountered a mirror, they touched the marks on their own faces, not the mirror, as if they understood that the reflection belonged to them. This simple observation launched decades of research into the distribution of self-awareness across species, and it raised a question that science is still carefully answering. What does it actually take for a mind to recognize itself? That question threads through everything else. It will carry us a long way from here. Gordon Gallup's chimpanzees were not trained to use mirrors. They were simply given one. At first, the animals treated the reflection the way most animals do, as a stranger. They vocalized at it, postured toward it, circled it with caution. But within a few days, something shifted. The chimpanzees began using the mirror to inspect parts of their own bodies they had never been able to see directly, the inside of their mouths, the top of their heads. And when Gallup applied a small odorless mark to each animal's face while it was anesthetized, the animals woke up, saw their reflections, and reached not toward the glass but toward their own skin. They had understood something. The reflection was them. This is not a behavior that most animals display. It is rarer than most people assume. Of all the species tested with variations of the mirror mark test since Gallup's original 1970 study, published in Science, only a small group has passed consistently: great apes, including chimpanzees, bonobos, and orangutans, and under certain conditions, gorillas. Outside the primates, bottlenose dolphins have shown compelling mirror-directed behavior, touching marked areas of their own bodies in front of mirrors when the marks were visible only through reflection. Elephants, specifically Asian elephants studied at the Bronx Zoo, have demonstrated similar responses. And in a finding that genuinely surprised many researchers, the Eurasian magpie passed the test. A bird, with a brain structured entirely differently from a mammal's, appeared to recognize itself. What exactly the test measures is still being carefully argued. Some researchers point out that failing the mirror test does not necessarily mean an animal lacks self-awareness. Dogs, for example, consistently ignore their reflections but show sophisticated responses to their own scent, a modality far more central to canine cognition than vision. When researchers created an olfactory mirror by presenting dogs with samples of their own odor versus altered versions of it, dogs spent more time investigating the altered version, suggesting they held some baseline representation of how they themselves smelled. The mirror test, it turns out, may be a test of visual self-recognition specifically, not self-awareness in the full sense. The instrument shapes what we find. Human infants do not pass the mirror mark test at birth. They don't pass it at 6 months or at 10. The ability emerges gradually, typically between 15 and 24 months of age, and even then it appears in stages. An infant might stare at a marked reflection with interest long before it reaches to touch its own face. The developmental psychologist Philippe Rochet at Emory University has proposed at least 5 levels of self-recognition in mirrors, ranging from confusion through contingency awareness, self-distinction, self-identification, and finally what he calls meta-self-awareness, knowing that others can see you too. The mark-touching moment is only one point along a longer arc. Have you ever watched a young child discover a mirror for the first time? What happens in the brain during mirror self-recognition has been studied using neuroimaging. The right hemisphere appears to play a stronger role than the left in visual self-recognition. Patients with right hemisphere damage sometimes fail to recognize their own faces in mirrors and photographs even when they can recognize other familiar faces without difficulty. This asymmetry is consistent with the right hemisphere's broader role in self-referential processing and in maintaining the spatial model of one's own body. The right side, it seems, knows the face better than the left. Primates who pass the mirror test also tend to show stronger performance on tasks requiring them to attribute mental states to others, to understand that another individual might hold a different belief, desire, or perspective. This overlap between self-recognition and what researchers call theory of mind is not coincidental. To model oneself as a distinct entity in the world, it appears, is closely tied to the capacity to model other entities as having inner lives too. The two abilities seem to share cognitive and neural infrastructure, and they tend to develop together both in human children and, to a measurable degree, across species. Knowing yourself and knowing others may be the same underlying skill expressed twice. Chimpanzees do more than recognize themselves in mirrors. Given prolonged access, they use mirrors for social display, for grooming, and, in observations that are difficult to interpret but hard to dismiss, appear to use them for something resembling self-examination in a quieter, more sustained way than their initial reactions suggest. Franz de Waal, in his work on primate cognition, noted that experienced mirror-using chimpanzees sometimes sit for extended periods regarding their own reflections with what looks, behaviorally, like attention rather than alarm. Whether this constitutes anything like contemplation in a meaningful sense, science is careful not to claim. But the behavior is there. The capacity for self-observation does not appear fully formed. It accumulates. One of the more unexpected findings connected to mirror self-recognition is its relationship to empathy. In both developmental and cross-species research, the ability to recognize oneself in a mirror correlates with the tendency to show consolation behavior, approaching and comforting another distressed individual. Chimpanzees who pass the mirror test are more likely to comfort others after conflicts. Human children who develop self-recognition earlier also tend to show earlier and more consistent empathy responses. The link is correlational and the mechanisms are still being worked out, but the pattern is consistent enough that researchers treat it as meaningful, as if the ability to locate oneself also creates a kind of imaginative access to the location of another. That connection between self-knowledge and compassion quietly runs deeper than most people realize. A mirror is, at its most basic, a surface that reflects. What makes it remarkable in a scientific context is not the glass but the behavior it reveals in the animal standing before it. Most of what the brain does with a mirror, the rapid self-other discrimination, the integration of visual and proprioceptive signals, the updating of the body map, happens below conscious awareness. The conscious recognition, when it arrives, is only the final signal that a great deal of invisible work has already been completed. The moment a child reaches to touch its own face is not where the self-awareness begins. It is simply where it becomes visible. The real process was already running well before the mirror arrived. The brain has never once seen the world directly. Every image, every sensation, every clear sense of where the body ends and the room begins, all of it arrives as electrical signal already translated, already compressed, already stripped of much of what made it real. What the brain does with that is not passive reception. It is active construction. And the self, the felt sense of being a particular someone, located in a particular body, is one of the things it constructs most continuously and most quietly. Neuroscientists describe this construction through a framework called predictive processing. The brain, on this account, is not primarily a device that receives and reacts. It is a device that predicts. At every moment, it generates a model of what is most likely happening, what the body is doing, what the environment contains, what sensations should be arriving, and it compares those predictions against the signals that actually come in. Where the prediction matches, the brain largely ignores the incoming signal. Where it doesn't match, the brain updates. The sense of a stable, continuous self is one of the brain's most persistent predictions, a hypothesis it has been running and quietly confirming your entire life. Errors in that prediction are what make certain illusions so revealing. In the late 1990s, the neuroscientists Matthew Botvinnik and Jonathan Cohen at Carnegie Mellon devised a simple experiment. A person sat with one hand hidden behind a screen. A rubber hand was placed in front of them in roughly the same position. A researcher stroked both the real hand and the rubber hand simultaneously with a small brush. Within minutes, most participants reported a creeping, involuntary sense that the rubber hand was their own, that the felt strokes and the visible strokes were happening to the same hand, even though they could see clearly that the rubber hand was artificial. Some participants flinched when a sudden threat was made toward the rubber hand. Their brains had updated the body map. A hand that was never theirs had become, briefly and measurably, part of them. What the rubber hand illusion demonstrates is that body ownership is not anchored in the physical body itself. It is anchored in coherent, cross-modal sensory prediction. When the timing of touch and vision align, the brain accepts the object as self. When they are made to conflict, when the strokes are applied asynchronously, the illusion collapses immediately. The self-model is flexible, but it is not infinitely so. It updates by evidence, and it withdraws by the same mechanism. The body you feel you inhabit is the brain's best current guess. The region most involved in tracking this body-self boundary is the insula, the cortical strip folded deep inside the lateral sulcus of each hemisphere. The insula receives input from the skin, the muscles, the joints, the organs, the full interior and exterior landscape of the body, and it integrates these signals into what researchers call the introspective self-model. damage to the right posterior insula can cause dramatic disruptions in body ownership, including a rare condition in which a person feels that one of their own limbs does not belong to them. The limb functions normally. The person may use it without thinking. But when attention is drawn to it, a sense of foreignness persists that cannot be argued away. The brain's self-model in those cases has a gap where the limb should be mapped. Ownership, not just location, is something the brain must actively maintain. The predictive self-model extends beyond the skin. Research by Henrik Ursin at the Karolinska Institute has shown that out-of-body-like experiences can be reliably induced in healthy participants using cameras, headsets, and carefully timed tactile stimulation. When a person watches a camera feed placed slightly behind and above their own body while receiving synchronized touch on their chest and back, many participants report the felt sense of self shifting toward the camera's viewpoint, of watching their own body from the outside. The brain, given consistent enough predictive signals, relocates the sense of self to wherever the coherent sensory model is being generated. The self does not live in the body. It lives in the model. That distinction is small in words and enormous in implication. The temporal dimension of the self-model is equally constructed. The brain does not experience time as a physicist would describe it, as an objective sequence of instants. It experiences duration, continuity, and narrative. The neuroscientist Anil Seth at the University of Sussex has described the self as a controlled hallucination, a predictive model so successful that it is never experienced as a model at all. This framing is not mystical. It means that the sense of being a continuous person, the same person who went to sleep last night and woke this morning, is an inference the brain draws from memory, from body signals, and from its own prior predictions. Continuity is not given. It is generated and quietly every moment. One of the more striking demonstrations of how fragile the self-model can be comes from studies of proprioception, the body's sense of its own position in space. When proprioceptive signals are artificially disrupted, using vibrating tendons that trick the muscles into signaling impossible positions, participants report bizarre distortions of body image. Arms that feel stretched beyond their actual length, limbs that feel misaligned, a body that feels altogether unfamiliar. These distortions are not imagined. They are produced by feeding the brain incorrect sensory data and watching it incorporate those errors into its best current model of the self. The machinery of selfhood is visible precisely when it breaks. What makes this framework scientifically important is not just that it explains illusions. It explains ordinary experience. The calm, stable sense of inhabiting a body, of being located in a room, of being the same person moment to moment. These are not facts that the brain simply reads off from the world. They are predictions it continuously makes, tests, and maintains. The self-model is updated thousands of times per second with incoming sensory data, most of which never reaches conscious awareness at all. What rises to the surface, what feels like the simple, obvious experience of being you, is the final, polished output of a process that never pauses, never announces itself, and asks for nothing in return. It runs, quietly and completely, every moment you are here. Somewhere above ordinary thought, the brain runs a second process. Not the thinking itself, the watching of the thinking. The part that notices when a memory feels unreliable, when a decision feels forced, when a word sits on the edge of recall and won't quite arrive. This capacity has a name in cognitive science, metacognition. And it turns out to be one of the most studied, most variable, and most consequential features of human self-awareness. Metacognition is not a single ability. It is a family of related processes, monitoring what you know, evaluating how confident you are, detecting errors before they produce consequences, and adjusting strategy when something isn't working. What makes it scientifically interesting is that it can be measured. Researchers can separate, in the same individual, how well someone performs on a task from how accurately they report their own performance. These two numbers, objective accuracy and metacognitive accuracy, often diverge in ways that are both consistent and revealing. The gap between them is where most of the interesting science lives. The brain region most consistently implicated in metacognitive monitoring is the anterior prefrontal cortex, the very front of the frontal lobe, a region that expanded dramatically in human evolution relative to other primates. In neuroimaging studies reviewed in Neuron and Nature Neuroscience, activity in this region correlates specifically with the accuracy of confidence judgments, not just with confidence itself. The brain, in other words, has dedicated neural machinery not merely for feeling certain but for tracking whether that certainty is warranted. The monitor and the monitored are separate systems. That separation has consequences that run through everyday life. Have you ever felt completely sure of something that later turned out to be wrong? The phenomenon most people know as the Dunning-Kruger effect describes a pattern first documented by David Dunning and Justin Kruger at Cornell University in 1999. Individuals with limited knowledge in a domain tend to overestimate their own competence in that domain, while highly competent individuals sometimes underestimate theirs. The popular version of this finding has been overstated and simplified over the years, but the core observation, that metacognitive accuracy requires domain knowledge to calibrate itself, has proven robust. You cannot accurately assess what you don't know until you know enough to recognize what you're missing. The monitor needs information to monitor with. Ignorance, in a precise sense, is partly invisible to itself. Metacognitive ability varies measurably between individuals even when baseline cognitive ability is held constant. Two people can perform identically on a memory test yet differ substantially in how accurately each reports their own performance. This individual difference has been linked to structural variation in the anterior prefrontal cortex, specifically to the volume of gray matter in that region. Larger volume in this area correlates with better metacognitive accuracy across a range of task types. The finding, replicated across several labs and summarized in a landmark paper by Stephen Fleming and Raymond Dolan at University College London, suggests that the capacity for self-monitoring has a measurable biological basis that varies from person to person as naturally as height or reaction time. The quality of the inner observer is not the same in every mind. Confidence and correctness are tracked by different neural circuits. Functional imaging studies show that regions involved in first-order performance, getting the answer right, and regions involved in second-order monitoring, knowing whether the answer is right, activate in partially overlapping but distinguishable patterns. The orbitofrontal cortex contributes to confidence signals. The anterior cingulate cortex is involved in error detection. The anterior prefrontal cortex integrates these into a metacognitive judgment. The whole system operates largely beneath conscious awareness, surfacing only its conclusions, the feeling of knowing, the sense of doubt, the quiet certainty that something is wrong before you can say what. Most metacognition never announces itself. It simply shapes what happens next. Sleep plays a specific and underappreciated role in metacognitive function. Studies examining performance after sleep deprivation consistently find that metacognitive accuracy degrades faster than raw task performance. A person deprived of adequate sleep may continue to perform at a near-normal level on certain cognitive tasks, while becoming significantly less able to accurately assess that performance. They feel more confident, not less, and that confidence is less calibrated. The anterior prefrontal cortex, among the brain regions most sensitive to sleep loss, appears to be one of the mechanisms behind this effect. Rest does not just restore performance. It restores the accuracy of the system that monitors performance. What sleep protects partly is the ability to know how well you are doing. Metacognition is not limited to intellectual tasks. The same monitoring capacity that tracks memory and reasoning also tracks emotion. Emotional metacognition, the ability to accurately identify, name, and reflect on one's own emotional states, is a distinct skill that varies independently of emotional intensity. A person can feel something strongly while having little accurate insight into what they are feeling or why. Research in affective neuroscience has associated this kind of emotional self-monitoring with activity in the medial prefrontal cortex and the anterior insula, both regions already implicated in the broader architecture of self-awareness. Emotional self-knowledge, in this light, is not a personality trait. It is a cognitive function, and like other cognitive functions, it can be sharpened or dulled by circumstance. There is a version of metacognition that operates on the scale of a lifetime rather than a single decision. The ability to look back across one's own history of beliefs and recognize patterns of error, to notice that you have been confidently wrong before in certain ways under certain conditions, draws on episodic memory, self-referential processing, and metacognitive monitoring simultaneously. It is one of the more demanding things the human mind can do, and it appears to be genuinely rare. Most people's autobiographical memory is selectively reconstructed in ways that preserve the sense of having been largely correct. The brain, as a rule, edits its own record in favor of the self-model it currently holds. The mind watches itself, but not always without bias. Most of what the brain knows about the self it learned from the body. Not from thought, not from memory, not from language, from the body's interior. The slow rhythm of the heartbeat, the tension across the diaphragm, the temperature of the skin, the fullness of the gut, the barely perceptible pressure of the breath moving through. All of it arrives in the brain as continuous signal, and all of it feeds into the construction of the self in ways that most people never consciously register. This inward listening capacity has a name in neuroscience: introspection. And it turns out to be far more central to self-awareness than its quiet operation would suggest. The body is not just the house the self lives in. It is part of what generates the self. Introspection refers specifically to the brain's perception of the body's internal state, not the feel of a surface against the skin, which is exteroception, but the feel of what is happening inside. Heart rate, hunger, nausea, warmth spreading through the chest, the vague unease before an identified emotion arrives. These signals travel primarily through the vagus nerve, the longest cranial nerve in the body, which runs from the brainstem down through the heart, the lungs, and the digestive tract, carrying information upward about the condition of the organs at every level. Roughly 80% of the vagus nerve's fibers are afferent, meaning they carry information toward the brain, not away from it. The body speaks far more than it listens. That ratio quietly reshapes what it means to say the brain is in charge. The capacity to detect one's own heartbeat without touching the pulse is used in research as a direct measure of introspective accuracy. Participants are asked to count their own heartbeats over a set interval without touching their body, and their count is compared to the actual measured rate. People vary enormously in how accurately they can do this. Some are nearly perfect, Others are consistently and substantially wrong. This variation is not explained by heart rate alone or by general attentiveness. It reflects a genuine difference in how well the brain is reading its own body, and that difference correlates across multiple studies with the richness and accuracy of emotional self-awareness. People who hear their own heartbeat more clearly tend to know their own feelings more clearly too. The insula, already mentioned as central to body ownership, is the primary cortical destination for interoceptive signals. Its posterior portion receives raw sensory input from the body's interior. Its anterior portion integrates those signals with cognitive and emotional context, producing what researchers describe as a felt sense of the body's current state. Not a number, not a measurement, but a quality of experience. It is in the anterior insula that raw physiological data becomes something closer to the feeling of being well, or uneasy, or alert, or spent. Antonio Damasio at the University of Southern California has described these integrated bodily states as somatic markers, background signals that quietly weight decisions, color perception, and shape the ongoing sense of who one is at any given moment. The body's condition is never neutral. It is always inflecting. The gut-brain axis, the bidirectional communication system linking the enteric nervous system of the gastrointestinal tract with the central nervous system, carries a volume of information that has only recently been appreciated in its full complexity. The gut contains around 500 million neurons, more than the spinal cord, and produces roughly 90% of the body's serotonin. Signals from the gut reach the brain via the vagus nerve and via hormonal pathways, and they influence mood, decision-making, and the tone of self-referential thought in ways that are measurable but not yet fully mapped. Research published in Nature Microbiology and elsewhere has shown that alterations in gut microbiome composition correlate with changes in anxiety, emotional regulation, and aspects of self-perception, a finding that continues to reshape how neuroscientists think about the biological substrate of the self. The self, in part, is assembled from signals that originate well below the neck. Posture contributes to self-awareness in ways that go beyond the obvious. Studies examining the effect of body posture on self-referential cognition have found that upright versus slumped positions produce measurable differences in confidence ratings, persistence on difficult tasks, and the emotional valence of self-directed thoughts. The mechanism appears to involve proprioceptive feedback signals from the muscles and joints that feed into the introceptive self-model, rather than purely social or psychological factors. The body's physical configuration is one of the inputs from which the brain infers the self's current state. Change the posture, and the inference shifts subtly but detectably. The brain reads the body's shape as a kind of evidence about who is present inside it. Hunger is another interoceptive signal with documented effects on self-perception and self-awareness. Research across behavioral and neuroimaging studies has shown that caloric depletion narrows attentional focus, reduces the quality of metacognitive monitoring, and shifts self-referential processing toward threat-relevant content. The self perceived under significant hunger is measurably different, more reactive, less expansive, more concerned with immediate need, than the self perceived in a fed state. This is not simply discomfort. It is a genuine shift in the parameters of the self model, driven by the body's interior reporting and integrated into the brain's ongoing construction of who is here and what matters. Physiological state and self-knowledge are not separate channels. They are the same signal. The vagus nerve is not only a carrier of body signals. It also responds to the brain's output, and that response feeds back into interoceptive awareness in a loop. Practices that slow breathing, for instance, directly alter vagal tone, the baseline activity level of the vagus, and measurably change both the physiological signals the brain receives and the quality of introspective awareness that follows. This is one of the few places in self-awareness research where a bidirectional mechanism has been documented with reasonable clarity. The brain shaping the body and the body shaping back in a circuit that never fully closes. The conversation between mind and body runs in both directions and never stops. This is a good companion for the quieter hours. Science that moves slowly enough to follow all the way down. What the body knows about the self and sends upward continuously is older than thought, older than language, older than the cortex that eventually learned to reflect on it. Introspection may be the most ancient layer of self-awareness, not the most refined but the most foundational. Before the brain could watch itself think, it was already listening to the body's slow report. The self did not begin in the mind. It began in the signal. Every human being who has ever lived began without a self. Not without a brain, not without sensation, not without the capacity to respond to the world, but without the particular organized loop of self-referential processing that would eventually allow the experience of being someone. That loop assembles gradually, over months and years, through a sequence that developmental science has been carefully tracing for decades. The story of how a mind comes to know itself is, in some ways, the clearest window into what self-awareness actually requires, because it shows step by step what the brain must build before the thing becomes possible at all. The absence before the arrival tells you something about the structure of what arrives. Newborns do not distinguish the boundary between self and world. In the earliest weeks of life, the infant brain has not yet developed the capacity to separate its own body from the environment surrounding it. Touch, sound, light, and internal sensation arrive as an undifferentiated field of experience. The developmental psychologist Daniel Stern, who spent decades studying infant perception, described the newborn's experience as an emergent self. Not the absence of experience, but a form of experience that lacks the organizing boundary between inside and outside that older minds take entirely for granted. The self, in Stern's account, does not appear suddenly. It crystallizes, slowly, out of a world that was not yet divided. Before there is a self, there is only the unbroken stream. One of the first signs of a developing self-boundary appears in how infants respond to touch. Experiments by Maria Papagiorgio and colleagues have shown that newborns as young as a few days old respond differently to self-touch, their own hand contacting their own face, than to the same touch applied by another person. The response to external touch is stronger and more sustained. The response to self-touch is partially suppressed, the same inhibitory mechanism that prevents adults from tickling themselves. The brain, even in its earliest weeks, has already begun distinguishing the signals that originate from its own body versus those that arrive from outside it. The boundary is being drawn one suppressed signal at a time. That suppression is among the earliest known markers of a self coming into being. Between 2 and 3 months of age, infants begin to show what researchers call contingency detection, a sensitivity to the relationship between their own movements and changes in the environment. When a mobile above a crib is attached to an infant's leg by a ribbon, babies in this age range quickly learn that their kicking causes the mobile to move, and they kick with visible pleasure. More tellingly, they become frustrated when the contingency is broken, when the ribbon is removed and the mobile continues to move on its own schedule. The infant is not just learning about cause and effect. It is learning that it is a cause, that its actions have a signature, and the world responds to that signature specifically. Agency, it appears, is one of the first concepts the self assembles around itself. The Rouge test, the mirror mark test adapted for human infants, was developed by Gordon Gallup and later refined by psychologist Beulah Amsterdam in the early 1970s. A small mark is placed on the infant's nose without their noticing, and they are then shown their reflection. Most infants do not reach to touch the mark on their own face until somewhere between 15 and 24 months of age. Before that window, they may smile at the mirror, reach toward it, treat the reflection as a companion, but not as themselves. The shift, when it comes, is not dramatic. A pause, puzzled look, a hand moving not toward the glass but upward, toward the nose. Something has changed in how the brain is reading the reflection. The moment is quiet, and it marks the crossing of a threshold that took nearly 2 years to approach. Language arrives into a self that is already partially formed, but it reshapes what that self can become. The emergence of personal pronouns, particularly the word I, in a child's speech typically follows mirror self-recognition by several months, appearing reliably between 20 and 28 months of age. Researchers studying this transition have observed that children begin using I only after they have begun to demonstrate self-recognition and self-directed behavior in other modalities. The word does not create the self-concept. It inherits it and then extends it, allowing the self to be named, referred to, compared, described, and eventually argued about. Once the self can be spoken, it can be examined in an entirely new register. Between the ages of 3 and 5, children develop what developmental psychologists call theory of mind, the understanding that other people hold mental states, beliefs, and perspectives that may differ from their own. The classic test involves a character who places an object in one location, leaves, and then the object is moved. Children below roughly age 4 consistently predict that the returning character will look for the object where it actually is, not where the character last saw it. They cannot yet hold in mind a belief they know to be false. The development of this false belief understanding marks a significant reorganization of the self model, one that now must accommodate not just a self, but a self among other selves, each carrying its own private interior. The self, at this stage, becomes genuinely social in its architecture for the first time. Adolescence brings a second major reorganization. The prefrontal cortex, the seat of self-referential processing and metacognitive monitoring, is among the last brain regions to reach full structural maturity, a process that continues into the mid-20s. During adolescence, heightened self-consciousness and social sensitivity reflect this transitional state. The self-model is being rebuilt at a larger scale with greater complexity, more social inputs, and a new awareness of how the self appears to others. The intense self-focus of adolescence is not vanity or instability for its own sake. It is the signature of a system under reconstruction. The scaffolding is visible precisely because the building is not yet finished. What the developmental arc makes plain is that self-awareness is not delivered whole. It is built, layer by layer, from the first suppressed self-touch in the hours after birth to the reflective adult capacity to examine one's own history, beliefs, and errors. Each stage adds something that was not there before. Each addition rests on the ones beneath it. The self that eventually sits quietly with its own thoughts at the end of a long day is the accumulated product of 2 decades of quiet biological construction, most of which happened without anyone noticing, including the person it was building. That it arrives at all is, on reflection, a considerable feat. The self does not develop in isolation. It never has. From the earliest weeks of life, the brain is not only building a model of its own body and its own states, it is building a model of other minds and using those models as a surface to reflect itself against. Other people are not simply features of the environment that the self navigates around. They are instruments through which the self is constructed, calibrated, and continuously revised. The social dimension of self-awareness is not a layer added on top of some prior solitary self. It is woven into the architecture from the beginning, present in the neural machinery long before the child could articulate what another person's presence means. To know yourself, it appears, you must first know that others are there to know you. The brain region most consistently implicated in understanding other minds is the temporoparietal junction, a region at the intersection of the temporal and parietal lobes, present in both hemispheres but particularly active in the right. This region is recruited when people reason about the beliefs, intentions, and perspectives of others, and it is also active during certain forms of self-referential processing, particularly when the self is being considered from an outside perspective, as in imagining how one appears to another person. The temporoparietal junction sits at the hinge between self and other, and its activity reflects how deeply those two things are computationally entangled. Knowing what someone else thinks and knowing how you appear to them use much of the same machinery. The sociologist Charles Cooley proposed in 1902 what he called the looking-glass self, the idea that a person's sense of self is fundamentally shaped by their perception of how others see them. What began as a sociological observation has since accumulated a substantial body of neuroscientific support. Neuroimaging studies show that evaluating oneself on social dimensions, attractiveness, competence, likability, activates the medial prefrontal cortex more strongly when participants believe their responses will be seen by others than when they believe the task is private. The social audience, even an imagined one, changes the neural signature of self-evaluation. The self-model is not generated once and stored. It is regenerated partly in every social context. The presence of others reshapes the process from the inside. Theory of mind, the capacity to model another person's mental states as distinct from one's own, shares neural infrastructure with self-awareness in ways that have proven difficult to fully separate. The medial prefrontal cortex, the temporoparietal junction, and the posterior superior temporal sulcus form a network that activates both during self-referential thought and during mental state attribution to others. Rebecca Sachs at MIT, whose work using neuroimaging helped map this network in detail, has shown that the temporoparietal junction specifically responds to the content of other people's thoughts. Not their actions, not their emotions, but the specific mental states they hold. The brain has a dedicated region for modeling what is inside another mind. That same region contributes to modeling what is inside one's own. The boundary between self-knowledge and other knowledge is blurrier in the brain than in experience. Empathy and self-awareness overlap in ways that are measurable and specific. Studies examining individuals with higher interoceptive accuracy, the heartbeat detection capacity discussed earlier, consistently find elevated empathic accuracy as well. People who are better at reading their own internal states tend to be better at accurately inferring the emotional states of others. The proposed mechanism, supported by work from Tanya Singer at the Max Planck Institute, is that the brain uses its own internal simulation system to model others' experiences. It generates a representation of what it would feel like to be in another's situation, drawing on its own introspective and emotional machinery to do so. Self-awareness and empathy are not merely correlated. They may share a common computational substrate. To feel what another feels, you may first need to be able to feel what you feel. Social isolation produces measurable changes in self-referential processing. Studies examining individuals in extended isolation, ranging from participants in solitary confinement research to volunteers in polar expedition simulations, document a consistent pattern. As social contact diminishes, the default mode network activity associated with self-referential thought becomes more repetitive, more ruminative, and less adaptive. The self-model, normally calibrated against the ongoing feedback of social interaction, begins to drift inward without the corrective pressure of external social information. Prolonged isolation does not simply change mood. It changes the quality and accuracy of self-perception in ways that are both predictable and difficult to reverse quickly once social contact resumes. The self requires other people the way a clock requires something to measure. The phenomenon researchers call social comparison, the largely automatic tendency to evaluate oneself relative to others, has a specific neural signature centered on the ventral striatum and the medial prefrontal cortex. When people receive information that appear has outperformed them, the ventral striatum shows reduced activity compared to learning of one's own equivalent success. This comparison process operates below the threshold of deliberate intention. People engage in social comparison constantly, and the results continuously feed into the brain's ongoing self-evaluation, adjusting the self-model's parameters for competence, status, and belonging in ways that accumulate quietly over time. Much of what the self believes about itself was learned by looking sideways. Cultural context shapes the architecture of self-awareness in ways that neuroscience has only recently begun to examine directly. Research comparing participants from collectivist and individualist cultural backgrounds on neuroimaging tasks involving self-description has found differences in which regions activate when people apply trait adjectives to themselves versus to close others. In some East Asian participants, the medial prefrontal cortex activated similarly for self-description and for description of a close family member, suggesting the self-model included social relationships as constitutive elements. In Western individualist participants, self-description and other description produced more distinct neural patterns. The self is not a universal constant. Its architecture reflects the social world it was built inside. The container shapes the thing contained. Language does not merely label the social self, it actively constructs it. The way a culture provides words for inner states, the degree to which emotional experience is considered private or shared, the narratives available for making sense of personal history, all of these linguistic and cultural structures influence the detail, the coherence, and the stability of the self-model the brain maintains. Research in cross-cultural psychology has documented that individuals from cultures with richer emotional vocabulary for certain states report more differentiated and nuanced awareness of those states. The self partly is made of the words available to describe it. What cannot be named tends to remain less known, even to the mind that holds it. Across all the variation, cultural, developmental, individual, one pattern holds with unusual consistency. The human brain is never not oriented toward other minds. Even in solitude, the default mode network runs simulations of other people, imagines their responses, replays their words, anticipates their judgments. The self that feels most private and interior is, neurally speaking, populated with others. To be self-aware in the full human sense is to carry inside the mind a whole quiet society, and to have been built piece by piece by the pressure of its presence. The self knows itself in part because others were always watching. There are moments when the self steps back without being asked. Not in sleep, not in unconsciousness, in the middle of full, absorbed wakefulness. A musician deep inside a performance. A rock climber moving across a wall with no spare attention for anything beyond the next hold. A programmer so locked into a problem that an hour dissolves without a trace. In all of these states, something measurable happens in the brain. The default mode network, that persistent engine of self-referential processing, goes quiet. Not fully silent, but substantially suppressed. The continuous murmur of self-monitoring, self-evaluation, and self-narrative dims to something closer to stillness. And the person inside that stillness often reports that it was among the most satisfying experiences they have ever had. The self, it turns out, is not always what makes experience feel rich. The psychologist Mihai Csikszentmihalyi spent decades studying what he called flow, the state of complete absorption in a challenging task where effort and action seem to merge. What he described phenomenologically, neuroscience has since begun to map structurally. Neuroimaging studies of experienced musicians, athletes, and performers in flow-like states show reduced activation in the medial prefrontal cortex and the posterior cingulate, precisely the regions most associated with self-referential thought. The brain does not stop processing during flow. It shifts processing almost entirely toward the task and away from the self that is performing it. The monitor steps aside, and something runs more cleanly in its absence. Efficiency in certain domains appears to be the reward for self-forgetfulness. Long-term meditators show a different relationship with the default mode network than non-meditators, and the difference is visible in both structure and function. Research by Judson Brewer at Brown University and others using fMRI has shown that experienced meditators, during open awareness meditation, display markedly reduced activity in the posterior cingulate cortex, a key default mode hub, compared to novices attempting the same practice. More striking is that meditators show increased functional connectivity between the anterior cingulate cortex and the posterior cingulate, a pattern associated with the capacity to notice when self-referential thought has arisen and to disengage from it without suppression. The skill being trained on this account is not the absence of self-awareness but a lighter, less adhesive relationship with it. The self is still present. It simply stops insisting quite so loudly. The default mode network does not only generate self-referential thought. It also generates mind-wandering, the spontaneous, largely undirected mental activity that fills the gaps between focused tasks. Research by Matthew Killingsworth and Daniel Gilbert at Harvard, drawing on a large-scale experience sampling study, found that people spend roughly 47% of their waking hours thinking about something other than what they are currently doing. More significantly, mind-wandering predicted lower reported happiness regardless of the activity being performed, a pattern the researchers described as the cost of a mind that has left the present. The default mode network, running its self-narrative in the background, appears to carry an emotional charge that focused, self-suspending engagement does not. A mind elsewhere is, on average, a mind less at ease. Anosognosia is the neurological condition in which a person is genuinely unaware of their own impairment. Not in denial, not minimizing, neurologically unable to perceive that a deficit exists. The most striking form involves patients who have lost the use of one side of their body following stroke or brain injury, yet sincerely report that everything is functioning normally. When asked to move the paralyzed limb, they may confabulate, generating a plausible explanation for why it did not move without any sense that they are doing so. The condition is most commonly associated with damage to the right hemisphere, particularly the right parietal and frontal regions, and it reveals something profound. The same brain systems that generate self-awareness are also responsible for updating the self-model when it becomes inaccurate. When those systems are damaged, the self-model persists unchanged, sealed off from contradicting evidence. The map does not update when the territory changes, and the person inside the map cannot tell. Depersonalization disorder offers a different kind of window into the constructed nature of self-awareness. People experiencing depersonalization report feeling detached from their own mental processes, their own body, or both, as if observing themselves from outside, as if the self has become a performance being watched rather than a life being lived. Neuroimaging studies of individuals with this condition show altered activity in the anterior insula and the anterior cingulate cortex, regions central to introspective self-awareness and emotional integration. The sensory signals are arriving normally. The integration that produces the felt sense of ownership, the sense that this experience is mine, is disrupted. Depersonalization is not a loss of perception. It is a loss of the attribution of perception to a self. The experience remains. The person who owns it temporarily withdraws. A related but distinct condition, derealization, involves a sense that the external world has become unreal, present but remote, visible but not quite inhabited. Both depersonalization and derealization can occur in otherwise healthy individuals under conditions of extreme stress, sleep deprivation, or sensory disruption, suggesting that the integration processes that produce normal self-awareness have a tolerance threshold. Push the system hard enough, and the seams of the construction become briefly visible. Most people who experience transient episodes recover quickly, but the experience, while it lasts, tends to be described in remarkably consistent terms across individuals who have never compared notes. The world is there, and I am watching it, and neither of us is quite real. The description is almost identical because the mechanism failing is almost identical. Certain anesthetic agents produce reliable disruptions of self-awareness that have proven scientifically informative. Ketamine, at subanesthetic doses, reliably produces experiences of self-dissolution and altered body ownership in healthy volunteers, and it does so partly by disrupting the normal balance of predictive processing signals in the cortex. The experiences it generates, a sense that the boundary between self and world has softened or dissolved, closely resemble reports from individuals in deep meditative states and from clinical cases of depersonalization. The convergence across such different pathways, pharmacological, meditative, neurological, towards similar phenomenology suggests that what is being disrupted in each case is a common underlying mechanism: the brain's maintenance of a bounded, coherent self-model. Different routes to the same quiet dissolution point toward the same architecture. Sleep itself, when examined carefully, reveals the self's dependence on ongoing neural maintenance. During the deepest stages of slow-wave sleep, default mode network activity diminishes substantially, and with it the narrative self, the sense of being a continuous person with a history and a future, recedes entirely. It does not vanish. Dreaming sleep brings its own fragmented self-referential activity. But in deep dreamless sleep, something very close to the cessation of constructed selfhood occurs nightly in every human brain, as naturally as breathing. The self that returns in the morning is not preserved somewhere intact during those hours. It is reconstructed, from the same materials, in the same way it has been reconstructed every morning of a human life. Each waking is, in a small and biological sense, a beginning again. What the disruptions collectively reveal, flow states, meditation, anosognosia, depersonalization, anesthesia, deep sleep, is that the ordinary, stable, continuous self is a maintenance project. It requires active neural work to persist. It is not the default condition of the brain. It is a specific achievement of the brain, one that most people sustain so effortlessly and so constantly that the effort never becomes visible. It becomes visible only when something interrupts it. And in that interruption, however brief and however strange, the true nature of what was running quietly all along becomes, for a moment, possible to see. There is a point in the science of self-awareness where the instruments go quiet, not because the questions stop being scientific, but because the questions arrive at something that current tools cannot yet resolve, and perhaps cannot resolve in principle. Neuroscience has mapped the regions, traced the networks, measured the delays, cataloged the disruptions. It has tracked self-awareness through development across species into disorder and dissolution. What it has not yet done, and what a growing number of researchers openly acknowledge it may not be equipped to do, is explain why any of this neural activity is accompanied by experience at all. Why there is something it feels like to be a mind that knows it is a mind. That gap between mechanism and experience is where the hardest problem lives. The philosopher David Chalmers named it the hard problem of consciousness in 1995. The question of why physical processes in the brain give rise to subjective experience. Explaining which brain regions activate during self-recognition, or how the default mode network generates self-referential thought, addresses what Chalmers called the easy problems. Not easy in the sense of being simple, but tractable in principle, solvable by the standard tools of neuroscience. The hard problem is different in kind. It asks why there is an inner life at all. Why the neural correlates of self-awareness are accompanied by the felt quality of being aware. No current scientific framework has resolved this, and several prominent neuroscientists, including Christoph Koch and Francis Crick in their collaborative work on consciousness, spent decades arguing that the neural correlates of consciousness could be mapped without the hard problem thereby being solved. The map and the territory here are separated by something the map cannot represent. The most influential scientific framework for understanding how consciousness arises in the brain is global workspace theory, developed by Bernard Bars and later extended into neuroscientific terms by Stanislas Dehaene at the Collège de France. The theory proposes that consciousness arises when information is broadcast widely across the brain through a network of long-range connections, made globally available, as opposed to remaining localized in sensory or processing modules. On this account, self-awareness involves the default mode network and prefrontal regions gaining access to this global workspace and holding self-relevant information in a state where it can influence processing across many other systems simultaneously. The theory has substantial empirical support, particularly from studies of what happens to neural broadcasting at the threshold of conscious awareness. What enters the workspace becomes known. What stays local does not. A competing framework, integrated information theory, proposed by neuroscientist Giulio Tononi at the University of Wisconsin, approaches the problem from a different direction entirely. Rather than asking which brain processes correlate with consciousness, it attempts to define consciousness mathematically, as a quantity denoted phi, representing the degree to which a system integrates information in a way that cannot be reduced to the sum of its parts. On this theory, consciousness is not a special property of biological brains. It is a property of any system with sufficient integrated complexity. This places integrated information theory in direct conflict with global workspace theory on several predictions, and the debate between them, conducted through neuroimaging studies, theoretical papers, and an unusual public adversarial collaboration organized in part through the journal Nature Neuroscience, remains genuinely unresolved. Two well-supported theories of consciousness currently make incompatible predictions, and the experiments that would clearly separate them have not yet been performed. The binding problem is a closely related challenge that sits at the intersection of perception and self-awareness. The brain processes different features of experience: color, shape, motion, sound, meaning, in anatomically distinct regions. Yet experience arrives as unified. A voice belongs to a face. A color belongs to an object. The self belongs to a body. How the brain combines separately processed information into coherent, unified percepts and into a unified self, without a central processor known to perform this integration, is a question that has resisted clean resolution for decades. Several candidate mechanisms have been proposed, including synchronized neural oscillations in the gamma frequency range, but no single account has achieved consensus, and some researchers argue the problem may require revising the terms in which it is currently framed. Something binds experience into wholeness. What it is precisely remains open. Functional neuroimaging, fMRI, e.g., MEG, has transformed the science of self-awareness by making neural activity visible in living, behaving brains. But it carries significant interpretive limits that are sometimes underappreciated in popular accounts. These tools measure proxies, blood oxygenation changes, electrical field fluctuations, magnetic signals. They do not measure neural firing directly. Their spatial and temporal resolution has improved substantially but remains coarse relative to the speed and scale of the neural events that generate experience. A region activating in a neuroimaging study is not a module performing a single function. It is a network node participating in multiple overlapping processes. And the same region can carry very different computational roles across different contexts. The precision suggested by colorful brain maps is often greater than the precision of the underlying measurements warrants. The images are clearer than the conclusions they can support. The question of whether artificial systems could genuinely be self-aware, not merely process information about themselves but have an inner experience of doing so, is one that current neuroscience cannot answer, partly because it cannot yet fully answer the question for biological systems. Large language models and sophisticated AI architectures can produce outputs that describe internal states, report on their own processing, and pass certain behavioral tests that would be taken as evidence of self-awareness in an animal. Whether any of this constitutes genuine self-awareness in the phenomenological sense, whether there is something it is like to be such a system, depends entirely on which theory of consciousness turns out to be correct, and on empirical questions about the architecture that no existing test can resolve. The behavioral surface of self-awareness and its experiential interior are not the same thing, and distinguishing them remains beyond current tools in any substrate. Certain anesthetic states have recently been used as a kind of natural experiment to probe the boundaries of conscious self-awareness. When patients are under general anesthesia, global workspace broadcasting collapses. The long-range neural communication that global workspace theory identifies with conscious access is measurably disrupted, and with it both self-awareness and conscious experience appear to cease. The predictability of this collapse, and its reliable reversal upon emergence from anesthesia, has strengthened the empirical case for global workspace theory. Yet it does not fully answer why the collapse of broadcasting is accompanied by the absence of experience rather than simply the absence of reporting. The correlation holds. The explanation for why the correlation holds at the level of experience is still being constructed. Mechanism and meaning remain, for now, two separate conversations about the same event. What is perhaps most striking about the current state of consciousness science is not what it has failed to explain, but how much it has clarified about the shape of the problem. A century ago, self-awareness was barely a scientific subject at all. It was a matter for philosophy and introspection, largely inaccessible to empirical methods. Today, it has anatomy, developmental stages, measurable individual differences, documented disruptions, and competing mathematical theories. The hard problem remains, but it sits inside a far more detailed scientific landscape than it once did, surrounded by findings that constrain what any eventual solution will have to account for. The edge of what science can say keeps moving. It has been moving for as long as science has existed. Before there were words for it, before there were theories about it, the thing was already running. Whatever self-awareness ultimately is, a controlled hallucination, a predictive model, a global broadcast, an integrated information structure, it did not appear in the world as a philosophical achievement. It appeared as a biological one, something that natural selection shaped, refined, and preserved across millions of years because organisms that modeled themselves survived in ways that organisms without that capacity did not. The science of its origins is incomplete, as all evolutionary science of cognition necessarily is. But the outlines are becoming clearer, and they point toward something older and more functional than the introspective richness we associate with the fully human version of the trait. Self-awareness, in its earliest form, was probably not about knowing the self. It was about predicting it. The evolutionary argument for self-awareness as a survival mechanism centers on the adaptive value of accurate self-modeling in social environments. An organism that can represent its own strength, hunger, fatigue, and emotional state, and predict how those states will influence its behavior, is better positioned to navigate competition, cooperation, and conflict with others of its kind. Primatologist Robin Dunbar at Oxford has proposed that the demands of complex social living drove the expansion of the neocortex in primates, with self-awareness emerging partly as a consequence of the cognitive machinery required to track and predict the behavior of multiple social partners simultaneously. To model others accurately, you must first have a stable model of yourself to compare against. The social world may have been the pressure that forced the self into existence. The capacity for self-awareness correlates across primate species with neocortical volume relative to total brain size, a relationship documented in comparative neuroanatomy and behavioral research and consistent with Dunbar's social brain hypothesis. Species with larger neocortical ratios tend to live in larger, more complex social groups and to demonstrate more sophisticated self-referential and other referential behaviors. The correlation is not perfect. Evolution rarely produces clean gradients, but the pattern is strong enough that most researchers treat social complexity and advanced self-awareness as co-evolved capacities rather than independent developments. The size of the group and the depth of the self appear to have grown together. Human self-awareness carries specific features that appear to be genuinely novel in evolutionary terms, even relative to other great apes. The capacity for autobiographical memory, the ability to mentally travel through personal time, recalling specific past episodes and imagining specific future ones, is associated with the hippocampus, the medial prefrontal cortex, and the default mode network working in concert. Endel Tulving at the University of Toronto, who first characterized episodic memory as a distinct memory system in the 1970s and 1980s, described this capacity as mental time travel. It allows the self-model to extend across time, not just a representation of who I am now, but of who I was and who I might become. No other species has been demonstrated to possess this capacity to the degree humans do, though evidence for limited forms of it exists in great apes and corvids. The human self is not just located in a body. It is located in a story. Default mode network activity during wakeful rest, the idle, self-referential processing that fills the mind when no external task demands attention, serves functions beyond mere mental housekeeping. Research suggests that this resting state activity is involved in consolidating self-relevant memories, simulating future scenarios, updating the self-model with recent social information, and maintaining the narrative continuity of personal identity across time. Far from being wasteful, the default mode's resting activity appears to be doing some of the most important long-term work of selfhood, integrating experience into a coherent ongoing account of who this particular person is and how they got here. The mind at rest is not idle. It is doing the slow work that wakefulness interrupts. The default mode network's activity during rest also changes measurably across a human lifespan in ways that track the broader arc of self-development. In childhood, the network's connectivity is still maturing, and its activity is less organized and less consistent than in adults. In healthy aging, certain default mode connections weaken, and this weakening correlates with changes in the coherence and stability of autobiographical memory and self-narrative. In conditions like Alzheimer's disease, the default mode network is among the earliest affected systems, its disruption preceding and predicting the erosion of personal identity and self-recognition that defines the condition's most distressing stages. The network that builds the self over a lifetime is also, in some conditions, the one that slowly carries it away. The structure that generates the self is the same structure that can lose it. Across the full arc of a human life, self-awareness is never static. The self-model that a 2-year-old holds fresh, undivided, anchored entirely in the present, is neurally and phenomenologically different from the self-model at 20, at 50, at 80. Each stage has its own characteristic relationship between the brain's monitoring systems, its interoceptive signals, its social inputs, and its accumulated narrative. What persists across all of them is not a fixed self but the process of self-modeling itself, the brain's continuous generation of a working representation of the organism it inhabits, updated with each experience, each relationship, each night of sleep, each morning reconstruction. The self is not a noun that the brain possesses. It is a verb the brain performs. Certain contemplative traditions arrived, through introspection and centuries of careful observation, at descriptions of the self that align with surprising precision with what neuroscience has since documented through entirely different methods. The observation that the self is constructed rather than given, that it is contingent on conditions and processes that can be altered, that the sense of a fixed, continuous self is in some sense a useful fiction maintained by ongoing mental activity. These are claims that appear in philosophical and contemplative literature long before the first fMRI scanner was built. Science did not need those traditions to arrive at its conclusions. But the convergence across such different methods and motivations is worth noticing. Different paths leading to the same careful qualification. What the mind eventually learns about itself, it may have been circling for a very long time. There is something that feels quietly significant about the fact that the brain, a physical system assembled by evolutionary pressure, running on electrochemical signals, structured by development and experience and social contact, generated somewhere in its processing the capacity to become curious about itself. not merely to function, not merely to survive and reproduce, but to look inward and find the looking interesting, to notice that noticing is happening. Whatever the ultimate explanation for that capacity turns out to be, the fact of it is already extraordinary. A universe that began without observers eventually produced organisms that observe themselves. That loop, from matter to mind to self-reflection, closed somewhere in evolutionary time without anyone deciding it should. Closed, and here we are still following its thread. The kind of science that carries the mind gently outward. This is what it was always meant to be. And when all the frameworks have been stated and all the regions named and all the disruptions catalogued, what remains is something simpler and harder to fully hold. The self-aware mind, lying quietly in the dark, using the very capacity under discussion to consider what it has just learned about itself, and finding in that recursion not an answer exactly, but a kind of spacious, unhurried wondering that feels, for reasons neuroscience is still working out, like exactly the right response to being the kind of thing that can wonder at all. If this kind of science is what you come here for, like and subscribe.